Hello everyone, welcome to lecture 5, the last lecture of week 11 of the course Power Network Analysis, in which we continue our discussion on transient rotor angle stability analysis of power networks. In short or precise, we call it as stability analysis. And in this discussion, we will we'll take up a method of reducing power network buses into buses which only represent internal EMFs of the synchronous generators for transient rotor angle stability analysis, because synchronous machines have to be represented by the internal EMFs in series with direct axis transient reactance XD dash. So how do we reduce the power networks with different buses into simpler buses so that the corresponding static equations involved in analyzing transient rotor angle stability, how they can be reduced, and that technique we will call as Ward reduction. And then we will extend this discussion for transient rotor angle stability analysis to a SMIB system in full, known as single machine infinite bus system. The last lecture, we had discussed at length about various aspects of swing equation, how swing equations exist for every synchronous machine in the power network, how with more renewable integration, H value tends to likely go down and the chances of stability or instability tend to go up. Details obviously will be discussed at length in the last lecture of this entire course or the module. We also understood different aspects of reducing down the number of swing equations based on coherency or the non-coherency aspects between the different synchronous machines. So in terms of Ward reduction, why do we need Ward reduction? Let's understand that a bit. So for transient rotor angle stability analysis, every synchronous machine is to be represented in terms of its transient internal EMF E, which is in series with XD dash, and the corresponding terminal voltage VT. Now what is VT? In terms of power flow analysis, we were only focused on the terminal voltage, specifically for synchronous generator buses, and we used to treat these buses as PV buses in power flow analysis. For fault analysis, we had to understand what are the worst case fault currents. So we did not retain ourselves only till the terminal of the generator or the bus. We went inside the machine terminal and represented every synchronous machine in terms of its internal EMF E, or in terms of E dash if I call, because E here is representing for transient situation. E double dash could be for the subtransient representation. And this internal EMF was in series with the subtransient reactance XC double dash in fault analysis. Since in transient rotor angle stability analysis, we have focused about how is this rotor angle delta in terms of the internal EMF with respect to the terminal voltage, how is that varying for different disturbances. So we essentially represent these different generators in terms of transient internal EMF and the corresponding transient reactance coming in. So essentially, the focus here in terms of transient rotor angle stability is on these buses rather than the terminal buses. And that's the reason why internal EMFs have to be represented, because if internal EMFs are not represented, we won't be able to estimate what is the angle delta, and we will only be able to get information of what is this phase angle appearing on the terminal of the bus, which may not be a correct representation of the swing curve or the rotor angle variation. And in conventional transient rotor angle stability analysis, the assumptions that we considered our load dynamics to be completely absent. We would represent all our loads as constant admittance or impedance type load. Dynamic equations representing rotor rotation are only used for analyzing transient rotor angle stability analysis. And in order to minimize the effort involved in doing exclusive power flow, because without power flow, we won't be able to get the phase or the terminal information. And once we don't know the terminal information, it is possibly not possible to directly get the internal EMF, having known the corresponding current injection from the generators into the different buses. So in order to find the initial equilibrium point which exists before a disturbance occurs, for which transient rotor angle stability analysis has to be done, without exclusive power flow analysis, the corresponding initial operating point or initial value of delta cannot be known. So is there a way of avoiding that? classical transient rotor angle stability analysis allows for such a representation, and that representation or reduction is essentially known as Ward reduction, in which the entire network is reduced only to machine nodes, and these machine nodes refer to the constant internal transient EMF E dash, where the magnitude of E is not changing. What can change is the corresponding angle delta only. And by representing the entire network only into these machine nodes, there is no need of doing power flow then for the entire network. It's again an assumption. One can always counter question and argue why is this assumption necessary. I would recommend, for the sake of understanding the concept, yes, this assumption might not sound logical, but to understand or have a premise, yes, it is useful for understanding that. In order to do more complicated analysis, specifically for multi-machine transient angle stability analysis, Ward reduction may completely be avoided and exclusive power flow may be done, and then corresponding initial operating condition may be obtained, but with a warning that transient rotor angle stability analysis is a limited time period of study. It is not a steady state period. So while doing our calculations, if the number of equations involved are so large that the time taken to solve them is so large, the event might come and go by and our analysis might still not give us any relevant solution, because of which the system corresponding corrective actions to maintain stability or avoid or avert instability might be lost. So that is the overall trade-off as power engineers to maintain corrective decisions or on corrective time with limited amount of computational effort involved. So let's understand what is Ward reduction. I hope the importance of Ward reduction I have been able to explain. To the intent is to avoid power flow analysis being done to the extent possible for reducing our computational effort. So every synchronous machine, we consider a fictitious generator bus, the bus which I have marked here, to be present between the internal EMF whose magnitude remains constant, the angle can change, and followed by that bus is the series transient direct axis reactance, after which we have this terminal voltage Vt. Similarly, for the load buses, we can have similar representation, but since load dynamics are involved, so load buses need not have these internal EMFs present with them. Considering these series transient direct axis reactance and all network lines which are present in the power network, we evaluate the overall bus admittance matrix with internal EMF buses also represented and transient reactances considered. After doing that, we can get this value of y dash. The process of evaluation of bus admittance matrix remains the same. Since we are focused only on generator buses, so we can categorize the buses into set capital G and set capital L, where the respective current injections, which is the vector I, is associating the corresponding bus admittance matrix y dash with respect to voltages at all generator as well as load buses. So if we break up this equation in terms of current injections at buses G and L, where capital G indicates the buses where internal EMFs are present for synchronous machines, and L represents those buses where only loads are present whose dynamics are ignored and they are all modeled as constant impedance or admittance load, then we can break the corresponding current injection into two distinct equations, where the first equation is representing injection of currents at generator buses in terms of voltage at generator buses and voltage at load buses. Now, what would be Vg? Vg is essentially a vector of all generator internal EMFs. So let's say E1 dash delta 1, E2 dash delta 2, and so on, where the magnitudes, they are fixed, they're constant, but delta 1 and delta 2, they can have variations. And similarly, VL is the generator buses voltage at all load buses. Since we are ignoring the dynamics at load buses, so load currents are not so important, or current injections at non-generator buses are not important for classical transient rotor angle stability analysis. The dynamics are all ignored. So we can assume that these currents are actually zero. So if this equation value becomes zero, then we can represent the load bus voltages in terms of generator bus voltages, and for this relationship to hold true, obviously this inverse should exist. That is, y dash LL should not be a singular matrix. Y dash LL in order to not be a singular matrix, there has to be a proper grounding present somewhere, because of which the corresponding bus admittance matrix should not become a singular matrix. Please recollect from the power flow analysis module where we were discussing bus admittance matrix that if the network is not directly connected to the ground with respect to which voltage or potential is being measured, then Y matrix tends to be a singular matrix. So to avoid having such a situation, it is assumed that the entire power network, which is having VG voltages at generator buses and VL at load buses, VG being the internal EMFs, there is some proper connection between the ground with respect to which these potentials are being measured. Assuming that such a potential reference exists and there is a proper connection between ground and the power network, so YLL dash will not be a singular matrix. YLL dash definitely will be a square matrix. Only singularity is to be avoided with proper grounding. So we can substitute VL in terms of VG and get an analogous equation which is completely in terms of currents and voltages at the internal EMF buses only. And essentially, the Y bus that we are getting, which is equal to YGG dash minus YGL dash, YLL inverse dash, YLG dash, it is the effective reduced bus admittance matrix of the power network with only internal EMF of the buses connected, transient direct axis reactances are already considered, and all network lines are also already considered. So if we focus or reduce our network into the generator internal EMFs, directly we can get an estimate of these load angles which I was talking about over here in terms of delta 1 and delta 2 without solving power flow equations exclusively, obviously based on the assumption that network dynamics and load dynamics are completely null or they are not present at all. So if we have understood that watt reduction aspect, coming to our powering angle equation which we were discussing in the last lecture also, we consider a case 2 basically where we have two synchronous generators represented by the corresponding internal EMFs E1 delta 1 and E2 delta 2 measured with respect to some common voltage reference. And we have already applied watt reduction, by which we have got the corresponding reduced Y bus. Since there are only two buses involved, the two internal EMF buses, so we have a 2 cross 2 Y bus matrix after applying watt reduction aspect in it. And using this watt reduction Y bus, we can express the power injections at these generator buses in terms of the load flow equations that we have already discussed and analyzed, where G11, G12, B12, they are essentially Y11 is this particular term, which is nothing but G11 plus JB11, and Y12 is G12 plus JB12, and similarly we have G21, B21, which are the corresponding real and imaginary parts of Y21 and Y22 respectively. Now, with these as our power injection equations, which are nothing new equations, but they are obtained from basic power flow equation analysis and the Y bus that we have got after watt reduction. Recollect or remember that in classical rotor angle stability analysis, one of the assumptions that was involved was network damping is completely ignored, which means network resistances are completely absent. They are not to be considered. Even if they are present, their absence, their values are not to be considered. So in such a case where the network is lossless in terms of resistances, recollect in terms of DC power flow, the corresponding G values, they will all become 0. If the values of G become 0, that means these terms, they are all absent. They have no contributions. And P1 and P2, they are effectively left only with minus B12, E1, E2, sine delta 2 minus delta 1. And P2 would be minus B21, E1, E2, sine delta 1 minus delta 2. So if we focus only on such a network which resistances are neglected because damping is ignored, Y bus becomes a pure imaginary matrix, and B12 and B21, they can be represented in terms of X, which is the transfer reactance, and P1 becomes nothing but negative of P2, where P1 is P max sine delta, P max is E1 E2 by X as shown over here in terms of E1 E2 and B1 B2. So delta becomes delta 1 minus delta 2, and the negative term here is incorporated inside, and hence delta 2 minus delta 1 is effectively minus delta. So we have P1 as E1 E2 by X sine delta 1 minus delta 2, which is also equal to minus P2. Please compare this equation with respect to the equations given in slide number 6. So effectively, what we are trying to understand is, since E1 and E2, their voltage magnitudes of internal EMF, they will not change because AVR action is neglected, and disturbance has happened in the network. So what would be the possible change that would bring in a deviation in P1, P2? The answer to that lies in the value of transfer reactance X. Because of disturbances, the corresponding transfer reactance X value is changing, which is deviating the electrical power output of the two synchronous generators, and correspondingly the corresponding rotor angle delta might also have deviation, and that is where the answer lies to the analysis behind transient rotor angle stability analysis. So to give an example, during a fault, the machine reactance itself varies. It varies from xg double dash to xg dash, and then in steady state it becomes xd, the corresponding saturated steady state value. And in terms of the equation that we have defined, which is P1 equal to P max sine delta, if we plot, so basically P max, it is varying under different disturbances. And if we plot P and delta for a fixed P max, we would essentially get the first half of the sine curve. There's a sine equation here. So we get the first half of sine curve where 0 degree or 0 radians and pi radians, they are marked here. And at steady state, since mechanical input is constant, it's steady state, so mechanical input or power is equal to the electrical power output. So PM and PE, they match. Rotor speed is exactly equal to synchronous speed. The rotor angle with respect to synchronously rotating frame is also not changing, and its initial value is delta naught, which is decided or dictated by the loading present in the power network, which is being fed by each of these individual machines. Delta naught is that operating point or initial equilibrium point that we need to know before we understand the importance of transient rotor angle stability analysis in terms of some disturbance, during which P max value itself might change because the X value is likely going to change. So the question now here is, we'll understand that in the next few lectures to come, but there is another interesting aspect here. If delta naught can be the initial operating point or equilibrium point before the disturbance has happened, why are we saying that PE marked over here represents the steady state operating point? Analogously or mathematically, there also exists an angle delta naught dash, which is pi minus delta naught, at which PE is also equal to P max sine delta naught, because sine of pi minus delta naught is exactly same as sine of delta naught. So why can't delta naught dash be an initial equilibrium point for a synchronous machine which is likely to undergo a disturbance for which transient rotor angle stability analysis needs to be done? The answer to that will be discussed in the next lecture at length, and there are well proven mathematical conditions which inhibit delta naught dash to be a steady state operating point. The steady state operating point will always be an angle between 0 radians and pi by 2 radians, and following a disturbance, delta naught, the angle of delta, which is this angle here, it will deviate from delta naught value, and depending on the disturbance, the post disturbance condition may or may not be same as delta naught and PM value in themselves. The question still remains, or the answer, my response to delta naught dash not being a steady state operating point is still a pending response, and we'll discuss that in the next lecture. We'll conclude this lecture with an example specifically on ward reduction, in which there is a 3-bus network given. The network is all lossless. The corresponding line reactances in per unit are all given. generators buses 1 and 2, they are having two synchronous generators whose respective transient axis direct axis transient reactances are also mentioned. And for transient rotor angle stability analysis, we have to use Ward reduction, where only the internal EMFs of synchronous generators remain connected. So essentially, instead of this synchronous generator, we have J.10 pu, which is the transient direct axis reactance of machine 1, and this machine is having an internal EMF E1 dash with an angle delta 1. Similarly, bus 2 or generator at bus 2 is represented by its corresponding direct axis transient reactance, whose value is J0.05 pu, with internal EMF being E2 dash at an angle delta 2, where delta 1 and delta 2 are being measured with respect to some voltage angle reference. And E1 dash and E2 dash, they are remaining constant. So our intent or idea is to reduce this entire power network where only these two buses or fictitious buses remain connected. Rest buses 1, 2, 3 and the respective lines, they are all removed and obviated or removed or completely nullified. So how do we do? As I was explaining in the previous slide here, in slide number 9, I have marked those fictitious buses as buses A and B, and I know how these different buses are now connected. So I evaluate my usual Y-bus matrix for this 5-bus network, where buses are A, B, 1, 2, and 3. And the evaluation of this Y-bus process is exactly the same as we discussed for power flow analysis. We try to find the corresponding admittances of respective lines A1, B2, 1, 2, 2, 3 and 1, 3, and then correspondingly find the 5 cross 5 element Y-bus matrix. So the corresponding evaluations, they are all shown here. So if we go by the usual discussion of Y-bus evaluation, the overall Y-bus with A, B, 1, 2, 3 as the row and column labels as per the bus numbers. This is my 5 cross 5 Y-bus matrix. Now in this 5 cross 5 Y-bus matrix, I want to retain only buses A and B as row and label columns. Buses 1, 2, 3 in row and label column should be removed. So essentially, capital G here, which is the set of all buses having internal EMFs, is A and B, and L index or L buses are 1, 2 and 3. So in a way, if I bifurcate or break this 5 cross 5 Y-bus matrix, then this 3 cross 3 lower half is YLL dash. The lower half present over here is YLG dash. The upper half here is YGL dash. And here I have YGG dash, which are also shown over here as per the corresponding row and column labels. So now since YLL dash, we know it's a 3 cross 3 matrix and it is not a singular matrix. As we can see, the corresponding rows, they don't add up to 0 in each of the 3 rows. So it's perfectly not a singular matrix. Only row 3 and column 3, they have addition 0. So it still is a full rank matrix. That means there's a proper ground reference present somewhere. Coincidentally, it happens to be this line or the transient reactance which acts as the ground reference, because with respect to terminal voltage, internal EMF E1 and E2, those two are being measured. So YLL dash inverse exists, and if we plug in those corresponding values as per the definition of Y-bus, this is our 2 cross 2 Y-bus matrix, which also indicates that there exists a fictitious series impedance between internal EMFs E1 dash delta 1, E2 dash delta 2, whose impedance is Z, and this impedance can be evaluated from the corresponding transfer reactance element, which is 0.231818. So that this is what the Ward reduction aspect is. Can there be a way to verify that this actually is the fictitious series impedance? Yes. Instead of doing Y-bus evaluation, one can use the usual network series parallel combinations of impedances. So if we see and we want to focus only on buses A and B, and we wish to remove buses 1, 3 and 2. So if we focus on, let's say, buses 1, 3 and 2, it appears that J.2 is in series with J.25. So effectively the impedance present on this path is J.45. J.45 happens to be in parallel with J.1, which is essentially what is mentioned over here in this particular term. And then we have J.1 and J.05 in series with the parallel combination of J.1 and J.45. So if we apply the series and parallel combination of these different impedances, the Z value turns out to be the same value, 0.231818, which we also got from the Ward reduction evaluation of retaining only buses A and B. So that in a way is a physical evidence, okay, that Ward reduction actually helps in reducing the network, even through, which is confirmed by the series parallel combination of impedances. That's all for this lecture. In the next lecture, we will understand the reason behind why delta naught dash cannot be a steady state operating point, and the answer to that lies in the concept of defining synchronizing power coefficient. And we'll also understand an important way of avoiding numeric integration for analyzing transient rotor angle stability analysis of SMIB system or two machine system which are either coherent with each other or not coherent with each other, and that criteria or technique is known as equal area criteria. Thank you.